Let's talk about equations. Here are some equations we know. 2 plus 3 is the same as 3 plus 2. Or 12 plus 19 equals 19 plus 12. Doesn't matter what order we write down the operands. And in addition, we get the same number. This is a general principle of addition, and we could write the general principle down by using letters in place of numbers. So x plus y is the same as y plus x. The idea also applies to adding three numbers. So if we have x plus y plus z, well, by this general principle, we can interchange the order of the operands for this plus sign, and we have z in the front, and then x plus y at the back. We can also interchange the order of the operands on this term, and now we have z plus y plus x. And now we've derived two new equations, one of which is x plus y plus z is the same as z plus y plus x. Of course, we already knew that we could add the numbers in any order, but this shows how that fact comes from the simpler one with just two numbers. Here's another equation that we know from arithmetic. X plus y plus z equals x plus y plus z. That is, if we have three numbers in the sum, we can group them either way. Group the first two and add on the last, or group the last two and add that to the first. We can use this equation to derive another one about adding numbers in any order. We derived this equation before. Let's look at x plus y plus z and apply that equation. It says that that's the same as z plus y plus x. And now, according to this grouping law, known as the associative law for addition, according to that law, we can group the first two terms instead of the second two terms. So we'll have z plus y plus x. So now we know x plus y plus z is the same as z plus y plus x. Again, something that we already knew, but we're seeing how it's derived from simpler ideas. So now we have two assumed equations and two derived equations. Let's try this again with some other equations. Here's two more equations that we know from arithmetic. Minus x plus x is the same as 0. If you add the negative of a number to the number itself, you get 0. And if you add 0 to a number, you get the same number back. Here's another equation that we can derive from those two. X is the same as x plus 0. That's just using the second equation backwards. And the 0 in this equation, of course, according to this one, it can be rewritten as minus x plus x. So now we have x plus, we're rewriting the 0 as minus x plus x. So now we have the equation x equals x plus minus x plus x. A more complicated equation, and maybe not a very interesting one, but it's something that we can derive from these two new assumptions. Now we add to the list of assumed equations three more equations we know from arithmetic. One is called the identity law for multiplication. It says that if you multiply a number times 1, you get the number back. The other one's called the null law for multiplication. It says if you multiply a number times 0, you get 0, regardless of what number it is. Let's add another law, the distributive law. It says that if you have x times a sum, x times y plus z, you can rewrite that as x times y plus x times z. We distribute the x across the y and the z in the sum. Or if you read it the other way, if you have two products and the left-hand factor in each product is the same, you can make that a product of that left-hand factor and the sum of the other terms. That's known as the distributive law. It establishes a connection between addition and multiplication. So if we add those equations, we're going to have 7 assumed equations. And, well, so far we've derived 3 equations for those. But let's think about a more interesting equation to try to derive. We know that minus 1 times minus 1 is 1. Multiplying 2 negatives, you get a positive. It turns out that we can derive this equation from the equations that we've assumed here. Let's see how that might go. If we're able to do that using our principle of reasoning that things equal to the same thing or equal to each other, then if we accept these 7 equations and the principle of reasoning, we must accept this new equation that we derive. So let's start from minus 1 times minus 1 and see where we can go. Well, minus 1 times minus 1, well, that's a number. If you think of it as the number x in this identity law for addition, you'll see that, if you think of it as the x here, you can rewrite it with that same x plus 0. It's the same number. Okay, so far so good. At this point, we can observe that we can also rewrite this 0. 0 can always be written as the negative of a number plus that number. And this number in this complement law for addition could be any number. For example, it might be 1. So now if we rewrite 0 in that way, we'll have in that place of 0 minus 1 plus 1. Okay, so far so good. Doesn't look like it's getting any better, but and these steps might look kind of ad hoc, but eventually we'll come to a point where it starts to look like we're making progress. Okay, now we have a sum of 3 terms. This term, minus 1 times minus 1, this term, minus 1, and this term, 1. They're grouped such that the second 2 terms are grouped together. We can also group it with the first 2 terms grouped together. So now we've got minus 1 times minus 1. That's one piece. We add on the second term, which is minus 1, and then we add on the last term. It's just a regrouping according to the associative law for addition. Okay, now let's observe that this minus 1 we can rewrite according to the identity law for multiplication. We can write it as minus 1 times 1. So let's do that. So we still got this minus 1 times minus 1 here. Now here, instead of just minus 1, we're going to have minus 1 times 1. And we're still going to have the plus 1 at the end. Okay, now look at this term here. It's a sum of 2 products in which the left-hand factor in each product is the same. So we can use the distributive law to factor that part out. And this will mean that we have minus 1 times, and this will be all one piece here, times the second factor here, which is minus 1, and the second factor, sum added to the second factor here, which is 1. And we still have the plus 1 at the end. Now things start to go a little more smoothly. We here have minus 1 plus 1, which according to the complement law, with x standing for 1, would have to be 0. So I can rewrite this term, this factor as 0. So I have minus 1 times 0. I still have the plus 1 at the end. Now, according to the null law for multiplication, anything times 0 is 0, so I can rewrite this term as 0. Now I can interchange the order of the operands here and get 1 plus 0. That's according to the commutative law for arithmetic. For addition, and now I can apply the identity law for addition and change this to a 1. So I started with minus 1 times minus 1. I found a new version of that, a new formula standing for the same number in each case, and ended up with a 1. So by our principle of reasoning, minus 1 times minus 1 must be the same as 1. A principle of reasoning and logic is often called a rule of inference. It's a rule that allows us to infer a conclusion from a known fact. The term axiom is commonly used to refer to assumptions that form the basis of a mathematical system. So what we are calling our assumed equations are the axioms of our system. Conclusions that can be derived from the axioms by applying the rule of inference are known as theorems. So we have a rule of inference, some axioms, and some theorems. One of the theorems, this last one, the minus times minus theorem, is important enough that we've actually given it a name. These other ones are not too interesting. The important idea to remember from this discussion is that equations allow us to rewrite parts of formulas. When we see a pattern of operations that matches one side of a known equation, we can replace that pattern by the one on the other side of the equation. We have to make sure that the numbers that match on one side are used in the same way as those variables on the other side of the equation. Furthermore, the matching items don't have to be simple numbers. They can be formulas instead of numbers. For example, the x in a formula like x plus y equals y plus x could actually stand for another formula. Maybe it stands for w plus z. So if x stands for w plus z, we can rewrite this formula as w plus z plus y equals y plus w plus z. For kind of perverse, we could even use the same letter. So x might stand for minus x. In that case, we would have minus x plus y equals y plus minus x. So any of the letters in a formula can stand for any formula that stands for a number or a number itself. We're going to use this principle of reasoning with many kinds of equations, not just equations where variables stand for numbers or numeric formulas. This discussion was just to practice reasoning with equations in the familiar context of numbers.